So you're at the park with your newfound kindergarten friend. She tells you she wants to ride the seesaw with you, and you're happy to oblige. But as soon as you both sit down at the handlebars, she is rocketed upward into the air like a phoenix rising from the ashes, while you sink lamely to the ground. Unfortunately, the path of the great phoenix is truncated because as soon as you hit the ground, the seesaw ceases to rotate any further. How might you both be able to feel the wind on your wings? Torque! So, torque is defined as a force multiplied by its distance from the pivot, which in your situation is the middle of the seesaw. Because the both of you are at the same position on the seesaw relative to the pivot point, your side, being that you are the more massive constituent to this situation, has a much greater torque than your friends. When taking both sides into account, there would be a total or net torque on the system. If you want any chance of having a bird's eye view of the park, you better get to rotational equilibrium. In other words, you want a total or net torque of 0 on the system. How might you do this? Well, look back at your torque equation. Because you are more massive than your friend, you are exerting a greater downward force on the seesaw. Gotta love gravity. Because changing your weight force all in the time you are at the park is a bit out of the question, you need to decrease your distance to the pivot in such a way as that the torque on your friend's side will then be equal to the torque on your side. Let's assign some values to this. Say you exert a force of 1200 newtons, that's the standard unit for force, on the seesaw, while your friend exerts only 560 newtons. Your friend sits at the very edge of the seesaw, which is 4 meters long in total. First, set up your equilibrium equation to have your torque, your weight force times your yet unknown distance, equal to your friend's torque, her weight force times her distance. Quick side note, because the pivot is located at the precise center of mass of the seesaw, you will not have to worry about its weight contributing to the situation. But don't get too hung up on the center of mass. This is just a point we physicists like to use to represent the entire concentrated mass of a given object. In other words, if you place some sort of pivot below this point, the object would balance. If it were the case that the pivot was not located at the center of mass, then all you would need to do is add the seesaw's torque value to whatever side the awkward pivot point made longer. You can rearrange your equilibrium equation by simply dividing your weight force so that your unknown distance is isolated on the left. Now, we just plug and chug. We know your friend's weight force, 560 newtons, as well as her distance from the pivot, exactly 1/2 the total length of the seesaw, so this would be 2 meters, and finally your weight force, 1200 newtons. So, after some number crunching, you need to sit 0.933 meters away from the pivot point. What are you waiting for? Take your newfound physics knowledge, scooch up on that seesaw to reach rotational equilibrium, and kick off into the clouds for a solid 3 seconds until it's your friend's turn to do so.